Hi guys, let's continue with our discussion of structure and bonding. In the first lecture we went over the basic atomic structure, review of atomic structure, and we began the bonding section. And we worked our way down to B here, structures with single bonds, and we put together a structure for CH4O. And I believe we came up with this structure here, and that's probably the only structure you will be able to come up with that formula. We see that's an alcohol. If you've covered the functional group handout or watched that video, this is a 1-carbon alcohol known as methanol. And so we can pick up here. And the next one there was to try to get a structure, come up with a structure with formula C2H6O. Now say here we're going to have two constitutional isomers that are possible. Now, if you've already watched the video on DOS, you can determine that this formula has 0 DOS because it's C2H6O. We can just ignore the O. 2 carbons, 2 times 2, 2n plus 2. There's lots of 2's there. That's 6. 6 H's max, and that's how many we have. So it is saturated. There is thus 0 degrees of unsaturation. No unsaturation. Thus we know that this compound will not have any double bonds or rings. Can't have it. Okay. Let's work on our whiteboard here. If you remember over here, I suggested we bond the heavy atoms together first. There's an oxygen there. Let's try carbon, carbon, and oxygen. How about that? Then next, if you remember, fill the valencies of your carbons with the available hydrogens. H here, H here, H here, H here, H here. And now each carbon has an octet, 2, 4, 6, 8, 2, 4, 6, 8, 8 electrons around each carbon through covalent bonding. We have one more H, and where might it go? We can then place it on the oxygen. We don't need to worry too much about bond angles right now. We'll discuss that later. How many valence electrons? First off, how many valence electrons in our formula? C2, that would be 8. 1 for each hydrogen, that's 6. And oxygen is 6. That would be 20 valence electrons. How many are we showing thus far? 2 electron covalent bond. 2, 4, 6, 8, 10, 12, 14, 16. And we need to show 4 more. That would be 2 lone pairs. And we recognize that the oxygen should have 2 lone pairs because common standard bonding for oxygen is 2 bonds, 2 lone pairs. And if you look at this structure, every heavy atom has an octet. Every hydrogen has a duet. That is a single bond. Standard bonding for carbon, standard bonding for oxygen. It meets the criteria for a good structure. This is a 2-carbon alcohol. It's a 1-carbon alcohol. 2-carbon alcohol is going to be known as ethanol. Because if you start learning your nomenclature, your prefixes would be meth, eth, prop, butyl, pentyl, hexyl, etc. 2-carbon alcohol, ethanol. We could just draw a line bond. You know, you might see ethanol just drawn like that, or we can show the lone pairs. So you see the two carbons here, and you see the three H's on this carbon. You see the two H's on that carbon. So this would be a line bond structure. So there's a good structure for that formula, but as was mentioned here, we can actually show two different constitutional isomers. We'll define that, but let's go back over here. Instead of bonding the three heavy atoms carbon-carbon O, you may have recognized that we could have bonded them carbon-oxygen-carbon. Then fill the valencies of carbon with hydrogens that we have. 6 available. That's 3, 4, 5, 6. Both carbons have octet, standard bonding, 4 bonds. Oxygen, 2 bonds. What about 2 lone pairs? Can we put 2 lone pairs? Yes, there's only 2, 4, 6, 8, 10, 12, 14, only 16 valence electrons shown. We need to show 20, 16, 18, and 20. And where this here is an alcohol, what we showed here is what functional group? Oxygen bonded to 2 plain carbons, it is an ether. This is actually called dimethyl ether. You'll learn that simple nomenclature in Organic 2. The 2 alkyl groups are both the same, so we can use dimethyl ether. Ethyl group, ethyl alcohol, or sort of shortened to ethanol. A little harder to draw a line bond here. I reckon you could. Problem is, it almost looks like it's, you know, it looks like there's something missing here. If it was ethyl groups, we could make it. Now it looks like it's sort of certainly vertices and carbons. That's why a lot of times we would maybe draw these like methyl groups. Variety of way to show compounds. So we have 2 different Lewis structures that are possible for this formula, and these are called constitutional isomers. Definition of those. Of course, isomers have the same formula, but there are different types of isomers. These have different connectivity. Things are connected differently. Here the 2 carbons are connected to each other. Down here they're not. They have different connectivity. Here the oxygen is connected to 2 carbons. Here the oxygen is only connected to 1 carbon. We can say bonded. The term connected or connectivity is used here typically when you discuss constitutional isomers. When we get to stereoisomers, those will have the same connectivity. Those will differ by spatial orientation of the groups. Okay, need to know different types of isomers. So we came up with 2 different constitutional isomers, and I think that's all you're going to be able to come up with. Yeah, I was thinking maybe we could do carbon, carbon, and then an oxygen that's sort of bridging and make that a 3-membered ring, but that's not possible. Because these compounds only have no DUS. Putting a ring here gives 1 DUS. If we tried to fill the valence of carbons, we'd put H and H, H and H, lone pair, lone pair. And there is no place to put the other 2 H's. But we sort of knew that wasn't possible anyway because we understand what DUS can tell us. This formula indicates that the compound has to be saturated, and both of these are saturated. That is, they have no degrees of unsaturation. Okay, let's try C. Now I've already kind of given it away here. Let's bring in something with a double bond. CH2O. There's your formula. I've already told you on the outline it has 1 DUS. Is that right? Let's ignore oxygen. 1 carbon. 2 times 1. 2N plus 2 equals 4. Four H is max. We only have 2, so we're missing 2. We can divide that by 2 and we get 1 DUS. Because every 2 H's we're missing is 1 degree of unsaturation. We're missing 2 H's compared to max. 1 DUS. So that's why we know we're going to have a double bond. Or a ring. But a ring is not possible here. Because a ring would have to require 3 heavy atoms. Okay. Systematic approach though. How many valence electrons? Carbon is 4, each H is 1, that's 6. Another 6 from the oxygen would be 12. Alright. What's next? Let's bond the heavy atoms together, the C and the O. Alright. Let's now then place the H's around carbon to fill its valence. 1, 2, and we don't have a third. This carbon needs an additional bond here, but we don't have another H. Alright, one step at a time. What should we do next? We have no more atoms, but we do have additional electrons because we've only used 2, 4, 6. We have 6 more electrons. That would be 3 lone pairs. Let's now fill valencies with lone pairs. But in this case, let's make sure we fill the valence of oxygen first. Because oxygen is most electronegative, and it's going to demand or want those electrons more than the carbon. It's inherently electron greedy. That's what electronegative means. That mainly comes from because the oxygen has more protons in the nucleus, and so the electrons are attracted greater to that nucleus. Let's fill the valence of oxygen. 1 lone pair, another lone pair, still not filled, 2, 4, 6, and 8. How many valence electrons? 2, 4, 6, 8, 10, 12. No more electrons to put in this compound. Are we done? No. We want to make sure, sort of our golden rule is, every atom has an octet. Of course, every heavy atom. Hydrogen can only have a duet. This carbon does not have an octet. Now the oxygen has an octet, 2, 4, 6, 2 electron covalent bond makes 8. But the carbon is not good. At this point, we're going to ask the oxygen to start sharing one of the lone pairs. And what we're going to do here is we're going to take this lone pair, I'm going to circle it, and we're going to move it in here with a mechanism arrow. Our very first mechanism arrow. Okay, here on August 10th. Now, what does this arrow mean? WDAM. What does arrow mean? Now, I'm not moving this lone pair and taking it and putting it on the carbon as a lone pair. I'm moving it in to become a bond between the oxygen and carbon. And we're going to show the resulting structure. And we're going to do a double-headed resonance arrow. Because really what we're doing here is resonance. And the result of that arrow, that is, what does arrow mean? We now have carbon. I'm not going to worry about bond angles. One bond between the oxygen, carbon and oxygen. This moves in to become the second bond. 2 electrons as a lone pair. Now 2 electrons as a second bond. 2 electron covalent bond. Leaving how many lone pairs on this oxygen? Well, leaving 2. And it doesn't matter where you place them at this point. I'm going to kind of place them symmetrical. Okay. This arrow movement gives this structure. We ask the oxygen to share one of its lone pairs. Okay. Not to give it away, but to share it through a 2 electron covalent bond with the carbon, creating a carbon-oxygen double bond. Now let's assess our structure. Now the carbon has 1, 2, 3, 4. 4 bonds, no lone pairs. Okay? Yes, that is 4 bonds. Standard bonding for carbon, 2, 4, 6, 8. 8 electrons around carbon in terms of an octet. The oxygen, 2 bonds, 2 lone pairs. Standard oxygen. 2, 4, 6, 8. 8 electrons around the oxygen as an octet. We now have a much better structure, and this is going to be your favored structure. That is a good structure for this formula. Remember we said we were going to have 1 DUS. Do you see the 1 DUS? Yes, 1 double bond. Okay. Before we move on, let's bring in charge. Now it's actually down on the outline where F is. Let's look at this structure over here. It's reasonable. It's not the best. All right, we're going to call this best / major. All atoms have octet. Now again, I'm referring to heavy atoms. Over here, the carbon does not have an octet. Not as good of a structure. But let's look over here. Let's consider this structure though. We have charges. Formal charges on the carbon and the oxygen. One way to recognize that is there's not standard bonding. And if you don't have standard bonding, you're most often going to have a charge. Not always. There's an exception to that. There are exceptions to about everything I say when I try to make sort of summary statements. But I think you'll agree we do like to hear some summary statements. Non-standard carbon. Is there a charge? How do you determine charge? Okay. Now you can look in your textbook for formula. You may have done this in Gen Chem, perhaps. It would have been great if you did. We start by asking how many electrons does this carbon own? Okay. The carbon owns one electron from each bond because this bond came from 1 electron from carbon, 1 electron from hydrogen. 1 electron from carbon, 1 from hydrogen, 1 electron from carbon, 1 from hydrogen. And if you count those up, there were 3 electrons from carbon. So I'm going to say it owns 3 Okay? Now, how many does the carbon supposed to own based on the periodic table? Okay? Usually owns 4 valence electrons. And that's valence electrons there. So it's missing one. Missing 1 electron. And if you're missing an electron, what should be your charge? Your charge should be positive. Okay? We can show a positive there. Now in organic chemistry, when we show charges, you need to show them very close to the atom, and usually you want to circle them. Now most chemists do that to keep it looking from like a kind of a stray plus sign or something. Circle your charges as close to the atom as possible. I know in Gen Chem sometimes you put the charges maybe up in a corner or something, but that's not the way we want to do it in organic. Now, how about the charge of the oxygen? How many does it own? Well, an atom owns its lone pairs outright, 2, 4, 6. And then it owns 1 of each bond. Okay? See, the carbon owned 1 of each bond. It owned 1 of these electrons, 1 of those, and 1 of those. Total of 3. Oxygen owns 6, plus 1 of those, 7. Owns 7 electrons. Of course, it usually, or supposed to own, how many based on periodic table? Oxygen is in group 6, usually owns 6. So here, the oxygen has 1 extra electron. And if you have an extra electron, your charge is going to be minus, because an electron is negatively charged. And the negative would be shown close to the atom and circled. Now, we knew that this had to be a net neutral molecule. All right? Net neutral. How did we know that? Well, because I didn't give a charge. If this was a charged molecule, I should have showed a charge with the formula. No charge shown, you must assume it's neutral. Unless I'm trying to trick you or something, and that would be just bad. Okay? If something has a charge, you need to show it not only with structure, but also with formula. It's net neutral. Here's our best structure. You see there's nothing charged, but this is net neutral as well. Now, we sort of arrived at all this sort of stepwise. All right? I could have put together a structure and just sort of thrown things together. You know, I could have just put H's anywhere. I could have ended up with here and then here. Of course, if I had done that, well, then I'm completely wrong, because this compound only has 12 valence electrons, and I've got 2, 4, 6, 8, 10, 12, 14. And so I'm wrong. You can't show 14 when there's only 12. So let's get rid of one of those. I could have said, well, that's my structure. Well, you have an octet around carbon, but you don't have an octet around oxygen, so that's not good. Now, you could have asked this to share, and we would have got that. But this is a better structure to show. Let's compare these two. Now, we're getting ahead of ourselves a bit, but it's worth comparing these. What's the charge of the oxygen here? And what's the charge of the carbon? Because neither one is standard bonding. The oxygen owns 1, 2, 3, 4, 5. It's supposed to own 6. It's missing 1. The oxygen is positive. The carbon owns 1, 2, 3, 4, 5. It's only supposed to own 4. It's got an extra one. It is minus. Compare these two. Which is better of these charge structures? Or charge separated structures? They're both net neutral. Would you rather have a minus on oxygen or carbon? And the answer is oxygen, because oxygen is more electronegative. It can handle a negative charge better. And so I just wanted to point that out. But guess what? That's why back up here I asked you to make sure you fill the octet of oxygen first with the lone pairs. That's going to lead to a better original structure, and then we can go from there. All right? But understanding electronegativity and why having minus on oxygen versus carbon is better, I just wanted to kind of point that out. Okay. Now, what type of compound did we make here? That's a carbonyl compound. That's actually formaldehyde. It's almost like a double aldehyde. You know, R group H aldehyde, it's got two H's. And we have a compound with a double bond. Okay, let's try a structure with triple bond. All right, HCN. How many DUS? Actually, we did that on the DUS page, didn't we? The DUS handout. Let's see, what do we do with nitrogen? We subtract an H. So if you get rid of the nitrogen and you subtract an H, we just have one carbon. And if you have one carbon and 2N plus 2, where N is 1, that'll be equals 4 H's max. But we have 0, so we're missing 4. For every 2 we're missing, that's a DUS. So how many DUS is this? 2 DUS. Again, you can look back at the DUS handout where we actually looked at hydrogen cyanide. 2 DUS, and we're actually going to see a triple bond here. Okay, systematic approach. Let's bond the heavy atoms together. Now let's do it down here with some room. CN, because we are dealing with HCN. Let's put the H's on carbon, but there's only one. How many valence electrons? Carbon's 4, H5, nitrogen 5, 10 valence electrons. I have 4 here. We can't put any more bonds to atoms, but we can put lone pairs. As I suggested up top, let's fill the valence of the more electronegative atom nitrogen first with lone pairs. 1 lone pair, 2 lone pairs, and 3 lone pairs for a total of 2, 4, 6, 8, 10 valence electrons. And now we can ask, do we have a good structure? And the answer is no, because the carbon does not have an octet. What can we do? We can ask nitrogen to share, and we can take these electrons and using a mechanism arrow we can move them in. It's like sitting here, moving them in to make another bond. Let's show what that gives. We now have 2 bonds between nitrogen and 2 lone pairs left. But the carbon still does not have an octet. 2, 4, 6. Nitrogen has an octet in both cases. So here, let's ask the nitrogen to share one more time. And we're going to take that lone pair and move it in as a 3rd bond. And we're using resonance arrows, okay, because these are resonance structures. And what does that arrow mean? Okay, it means we're making a 3rd bond, and we want to show that. And we end up with that structure. Now let's assess it. Now the carbon has 2, 4, 6, 8 octet, and the nitrogen still has an octet. 2, 4, 6, 8. And this is a good structure. This would be our best major resonance structure. Mainly driven by the fact that both heavy atoms have octets. So we can systematically arrive at a good structure as opposed to just randomly trying to generate a good structure. Now, while we're here, let's practice our charges. What's the charge of the carbon here? How many does it own? One of each bond. It owns 3. It's supposed to own 4. It's missing 1. That's a positive charge. The nitrogen owns 2, 4, 5, and 6. It's only supposed to have 5. It's got an extra electron. It is thus minus. We expected charge because this is non-standard bonding for both of those atoms. By the way, in our final structure, this is standard bonding. Carbon has 4 bonds, no lone pairs. Nitrogen has 3 bonds, 1 lone pair. Over here, what's the charge of this carbon? This carbon owns 2 electrons, 1 from each bond. It's supposed to own 4. That means it's missing 2. It is a 2 plus. Nitrogen owns 2, 4, 6. One of those 7. It's supposed to only own 5. It's got 2 extra, and so that's 2 minus. HCN is a net neutral molecule. There's no charge shown with the formula. Okay, we may need to end here soon. Resonance. Definition of resonance is shown. All right, please read the definition of resonance. We've been showing resonance here. And I'm going to end this video here at this point. Functional groups is next on the handout, and that's covered in a separate video. And the next topic will be Roman numeral 4, and we will get into hybridization and geometry. Okay guys, so that's some additional looking at standard bonding from the first handout, first page.